Good day, everyone. So today we shall be looking at another topic titled radioactivity. Radioactivity. So without wasting much of our time, let's dive into this topic. When you talk about radioactivity, you are talking about something they're actually familiar with. Look at this video. Can you see this object gradually reducing? Okay, so that is exactly what we are talking about today. When a substance is reducing in size gradually on its own, spontaneous reduction, we target a radioactive substance. Now, radioactivity is just the spontaneous decay or disintegration of the nucleus of an atom, okay, whereby emitting some particles like alpha particles, beta particles, gamma ray, and some other time with nuclear energy. So when this occur, then you say radioactivity has taken place. Okay, so when it occurs on its own, it is called a natural radioactivity. But when it is influenced by man, then it is known as artificial radioactivity. Okay, now let's see how these particles that are obtained when a radioactive substance decay. Let us see the laboratory experiment on how these particles are obtained. Let's see this video on this. Now, when a radioactive substance is placed in an object, okay, in a lid here, and then you could see that it begins to emit particles. One is blue, that's the gamma particle. One is red. One is blue, that's beta particle. One is red, that is gamma particle, and the other green is alpha particle. This, you could see that the alpha particle deflected towards the negatively charged plate, showing that the alpha particle is positively charged. And you observe that the beta particle, the blue one, deflated toward the positive charge plate, showing that the beta particle is negatively charged. And then the red one, which is the gamma ray, did not show any deflection. It shows that it has no charge. Now, the alpha particle also has a very low penetrating power, and that is why it could not penetrate the paper here. You can see it. You could not penetrate because its penetrating power is low. But that of beta has a higher one. You could see that the beta particle could penetrate the paper and then was stopped by aluminium object. That means that it also has its own limitation, but it has higher penetrating power than that of alpha particle. But the one gamma particle penetrated the paper, penetrated the aluminium, but could not penetrate the lead. So among these three particles, the gamma particle has the highest penetrating power. Now, aside from that, we could also say that the alpha particle move with almost 5 to 7% speed of light. Okay, it moved. You could see that. You could see it. You could see the way it was just moving. That the alpha particle. So it moved with almost 5 to 7% speed of light, and it has very heavy ionization. That means it can ionize. It can break atom into their ions. While beta particle has approximately speed of light, that means faster than alpha particle, then gamma particle is the fastest. Gamma rays actually move with the speed of light. On speed is it move with the speed of light. Okay, so these are the characteristics of the three particles that are emitted when an object spontaneously decay, which we call radioactivity. All right, so moving on, let's look at the half-life and decay constant. Now, this radioactive substance on their own decay, but when they decay, they have remnant, right? Now, the half-life actually of a radioactive element is the time taken for the half of that atom initially present in the element to decay. The time it takes for the half of that element to decay or to disintegrate is known as the half-life of that radioactive element, and it's represented with capital T or capital T subscript 1/2. Then decay constant is defined as the instantaneous rate of decay per unit atom of a substance. Okay, we use this symbol, okay, to represent decay constant. So it's defined as the instantaneous rate of decay per unit atom of a substance. Now, by formula, the relationship between half-life and decay constant is this. That is half-life, which is T, equals to 0.693 over decay constant. Another formula that is used in this radioactivity is this: N equals to N naught e raised to the power minus decay constant times T, where the N naught represents the number of atoms present before decay begins to occur. So the number of atoms present at time 0 when the radioactive substance is here to decay, and Yn is the number of atoms that is remaining at a particular time when decaying is occurring. Then another formula is capital A equals to A naught e raised to the power minus lambda. That symbol is called lambda T. Now, the A here represents activity, or what we call decay rate. So the A naught is initial activity before disintegration begins to occur, while the A represents the decay rate at a particular time T. So these formulas are very key for us to be able to solve problems in radioactivity. All right. Now let's see an example. A certain radioactive element has a half-life of 10 years. How long will it take to lose 7/8 of its atom originally present? And 2, how long will it take until only 1/4 of the atoms originally present remain unchanged? Okay, so let's take out our parameters. In the question, we are told that half-life is 10 years. That means our capital T is 10 years. Of course, when there is no decay, the total number of atoms is a whole. That's 1. That's N naught when there is no decay occurring yet. Now, the N is the remaining number of atoms after decay has occurred. We are told that 7/8 of the atom has been lost. That means we have to subtract 7/8 from the whole. So the remaining atom after some atom have lost, after 7/8 of atom has been lost, is 1/8. That's 1 minus 7/8. So now we have to find the time it took the radioactive element, okay, to decay to 1/8. So the time it took the radioactive element to lose 7/8, we can say it that way, or the time it takes the radioactive element to have a remnant of 1/8, either of them. But we are looking for we are looking for the time for the object to decay to 1/8 or to lose 7/8. Either of them is correct. Now, firstly, we need to get our decay constant. That means our lambda. By formula, lambda is 0.693 over T. T has been given to us as 10 years. So 0.693 over 10 will give us 0.0693 per second. Take note that the unit of decay constant is per second. Okay, but remember that we are looking for the time it takes the element to be reduced to 1/8 or to lose 7/8. So using this formula, our N has been given to be 1/8. We have obtained to be 1/8. So substitute that. Then our N naught, which is 1, then E is to power. Our lambda we have obtained to be 0.0693. Then our T. Now, if we simplify this with your calculator, where the E there represents your natural logarithm, then T there will give us 30 years. So we've solved the question 1. that the time it takes for the radioactive element to lose 7/8 of its atom is 30 years. It will take 30 years for 7/8 of the atom to be lost. Second question says, how long will it take until 1/4 of the atom originally present remain? Now, here in this case now, the remaining element, or the remaining atom rather, okay, is 1/4, and they're asking us the time it will take for the object to reduce to 1/4. So our n in this case 1/4, our n naught still remain 1. So using our formula of capital N equals to capital N naught e raised to the power minus lambda t, we substitute our value where our n in this case is now 1/4. We have 1/4 equals to our n naught is 1, our e still remain our natural logarithm, and then we substitute our lambda as well. And from there, if we simplify the calculator using your natural logarithm, we have our t to be 20 years. So it will take 20 years for the radioactive element to have 1/4 of its atom remaining. Okay, all right, now let's talk about in details type of radioactivity. I said earlier that when this radioactivity occur on their own, it is not a natural radioactivity. So this is the spontaneous disintegration of the nucleus of an atom, during which alpha particle, beta particle, or gamma particle or gamma rays are emitted, including heat. Sometimes heat does not go with it, but sometimes heat is released. Now, example of this is uranium. Uranium naturally decay to give us thorium and alpha particle. Alpha particle has been obtained to be an atom called helium. So when we talk about alpha particle, we are referring to helium. And of course, the atomic number of helium is 2, while the mass number is 4. Now, when uranium naturally on its own decay, it reduces toward thorium, which has an atomic number of 90. Now, in our chemical equation, we know that the equation must be balanced. The total number of the total number on the left must be equal to the total number of the right. So on the left here now, the subscript, which our atomic number here, is 92. On our right now, we have 90 plus 2 here, making 92. So the point here is that uranium has disintegrated to become thorium and then an emitted alpha particle. So this is natural radioactivity because on its own it's decay. And for carbon too, carbon decay to become nitrogen, and also it lost beta particle. Beta particles are negatively charged, and we call them electrons. Just like we call alpha particle helium, we call beta particles electrons. So for the natural decay of carbon, it decayed to turn into nitrogen and emitted beta particles and also released some nuclear energy. For radium naturally decayed to turn into radon and and emitted alpha particles as well. So ensuring that the equation is balanced, 86 plus 2 as the atomic number will give us 88, and that's 88 on the right hand side here. On the left hand side rather. On the right hand side also, the mass number of radon is 222, plus the mass number of helium is 4, that will 226, and that gives us 226 for radium on the left side. Now, if those radioactive substances are now induced by exposing them to neutron, by bombarding them with neutron or alpha particle, then we say the process is called artificial radioactivity. It is a kind of radioactivity that occurs when a radioactive substance is induced by irradiation using either neutron or alpha particle. So uranium now, remember when it was natural, there was nothing that was bombarded with it. But now artificially we want to allow it to decay. Neutron was bombarded with it. And when that was done, you could see that it was broken down into barium, krypton, and then some other neutron were also emitted. So that's what happened here. So when neutron or helium alpha particle are bombarded on a radioactive substance, this occur. Barium, for uranium and barium, it produces barium, krypton, and some neutron. Okay, the same thing for nitrogen. When nitrogen was bombarded with alpha particle, it emits, it produces oxygen and hydrogen. Okay, now whenever you bombard neutron with a radioactive substance, and that radioactive substance produces another radioactive substance that is just like it. In this case, you could see sulfur was bombarded with neutron and it still produced its isotope. Then we say the isotopes is called radioisotopes. Radioisotopes are isotopes that are produced as a result of bombarding them with neutron, okay, to produce the isotope. Now you could see here sulfur was having an atomic number of 16, mass number of 32 before bombardment took place. But after bombardment with neutron, it became mass number became 33, from 32 to 33, and the atomic number remained the same. Of course, we know that isotopes are elements of the same atomic number but different mass number, and then it releases gamma ray. Okay, so that was the two type of radioactivity that we have: the artificial one, the one that is induced by man, and then the second one, which is the natural one, the one that occur spontaneously on its own. Okay, now let's now talk about nuclear fusion and nuclear fission. Nuclear fission is not far from what we have been talking about since. Look at this uranium again. We said earlier that this is natural radioactivity because on its own it broke down into thorium and releases alpha particle. Now, when a radioactive substance splits into two approximately equal parts, you could see thorium and uranium are almost having the same mass. So when a radioactive substance split into two equal parts and also release some energy, then we say this is called fission. Okay, now you could see that uranium here has been split into thorium and then releases alpha particle. So this is called what? This is called fission, the splitting of radioactive substance. Okay, now fusion is the reverse. Fusion, nuclear fusion, is a nuclear process that occurs when two or more light nuclei combine or fuse together to form a heavier one. Okay, in this case, now you could see when we combine two deuterium together to give us tritium, then this is called fusion. All right, and then with some release of neutron and nuclear energy. So they are just the reverse. So fusion is just combination of two or more lighter nuclei to form a bigger one, while fission is what? Is the splitting of the nucleus into two parts. Okay, now advantages of fusion over fission. Firstly, fusion is more easily achieved with lightest element. Okay, so you can easily achieve fusion because you just need to bring two light elements together to form a bigger one. Okay, unlike fission, it's more difficult, it's easier to join than to break. So fission is more difficult than fusion. Again, the raw material you need for fusion, okay, are more readily cheap than that of fission. That's another advantage of fusion over fission. So the material are cheaper to get. Then lastly, the process of fusion is less dangerous than that of fission. Okay, so these are the three advantages of fusion, nuclear fusion over fission. Now let us talk about some of the uses of the nuclear energy that we have or we obtain from radioactivity. Firstly, the nuclear energy is used to power some plants that generate electricity for us. We also use this fission, okay, in radiotherapy, and then we use radioisotopes we obtain from nuclear plant as tracer and preservative, and also we use nuclear energy to power spacecraft, ship, and submarine. All right. So this is where we are going to be drawing the curtain today. Till I come your way next time.